Very happy to have Brian Cole here from Columbia University today. Brian did his PhD at MIT and has been at Columbia since. He's done a lot of experiments at Brookhaven with the accelerator there, studying nuclear collisions, and now does the same at the LHC at higher energy. And so really leading the program out there, and he'll be telling us today about those experiments. So, thanks.
Okay, all right, thank you, Andy. So it's a really pleasure to be come downtown and have a chance to tell you about the physics that we're doing. I have collaborators on this wonderful experiment at the LHC. It's a behemoth, but not only is it it's probably the largest piece of experimental apparatus ever built by mankind, but also performs amazingly well. And so I will be telling you about work that I'm doing at the LHC within the context of the Atlas experiment. And in fact, I have the privilege to actually interact with some of the people here as well carrying out that experiment. To give you some sense of what we're doing, I first want to use an analogy with something that you all know about, which is the universe and our understanding of how it began. So, way back early in time, something happened that we still don't completely understand. There's a period, we're pretty sure now, of inflation, and then after that, the universe expanded and cooled. And in fact, I want to highlight a period not long into the evolution of the early universe, about 10 microseconds after the Big Bang. There was a period where the universe was in a temperature range where the degrees of freedom were quarks and gluons, at least the predominant degrees of freedom. And then as the universe cooled, those combined into particles that we call hadrons. I'll say more about this. And ever after, the universe has lived in a world without free quarks and gluons. Now, one of the interesting things about the universe is that we're looking way out here, and we try to look back in time to understand what happened in the early universe. And in fact, we've made in physics tremendous progress, even from the time that I've been a physicist, in understanding the early universe, because we can do measurements like this of the cosmic microwave background fluctuations. We can do essentially a Fourier decomposition, really, in multiple moments of this, and look at the power spectrum as a function of the angular scale and get some really amazing experimental results, but then also amazingly precise description of that with what's called the concordance model, and obtain what I think is essentially ridiculous precision on parameters of the universe, at least compared to where they were 20 years ago when I was a young student. And the lesson from this is that, in fact, even though our vision of the early universe is disguised and, in a sense, influenced by the later evolution of the universe, we're still able to infer a tremendous amount by looking back in history. So that's relevant because what I'll be telling you about is, in a sense, a similar set of problems where instead of the Big Bang, we create what sometimes people call little bangs. So this is an event display of a single collision between lead nuclei at the LHC at the top energy that we can do that right now. So this is the equivalent of 7 TeV in proton-proton collisions. This is an event that was recorded soon after the start of the first lead-lead run at the LHC in 2010. What's shown in here is basically a display of data that we've taken with some kind of reconstruction. The lines here represent charged particles that we can reconstruct in the tracking detectors of Atlas. There are about 10,000 charged particles in here. The color blocks on the outside represent energy deposits above some threshold that we put on so that we only look at high energy deposits. And you can see lots of energy coming out even with that threshold. But in particular, you can see lots of energy here and here. And if you unfold this energy distribution into 2 dimensions, you see this, and these 2 spikes correspond to things we call jets, which are the products of quarks that underwent a very high momentum transfer scattering in the initial state and then turned into lots of final state hadrons. This is physics that...
The question, 2 dimensions or 2 angles?
Yes, actually, so this is essentially, we call this pseudorapidity. It's essentially a transformation of the polar angle. I'll say a little bit more about that later, and then this is azimuthal angle, right? So it's essentially an unfolding of this into a flat plane azimuthally and in polar angle. This is physics that's actually near and dear to my heart. I actually do most of my work on jet physics. I'm not going to say so much about it today because there's actually so much going on in this physics that I have to take a very focused view in order to tell a story. But I'll come back and say a little bit about this at the end. Now, you can ask the question, why do this? Because particle physics is already complicated enough. Why make it that much more complicated by colliding nuclei? Well, one way to think about this is that we know that there are 4 fundamental interactions in nature, right? So the gravity, strong interaction, electromagnetic interaction, and the weak interaction. But if you think about the way we study the fundamental interactions, in fact, almost everything that we experience every day is determined by the electromagnetic interaction. And in fact, most of the things that we do in the laboratory, studying atomic physics, and actually, let's say laboratories maybe here at Columbia as opposed to at CERN, we're studying things determined by the electromagnetic interaction, doing condensed matter physics, atomic physics, and the electromagnetic interaction in its manifestation has tremendously interesting and mysterious properties, but it is actually the simplest of all the fundamental interactions. And so suppose you ask the question, what would matter composed of particles that interact strongly look like, and how different would they be compared to the matter that we see with the electromagnetic interaction? And that's a fundamental question that we could ask and answer through the measurements that I'll be describing. Now, to understand why that might be an interesting question, let's talk a little bit about the strong interactions. So sort of at a glance, one picture of what makes them a little bit different. Electromagnetic particles interact through their charges. Charge is a scalar quantity for electromagnetic interactions. But in the strong interactions, there's a charge that we call color that quarks carry. And that determines the interaction among the quarks. But there's this thing called the gluon, which is the analog of the photon that, at least at the fundamental level, is the carrier of the strong interaction. And the thing that's different about the strong interaction and the electromagnetic interaction is that the gluon also carries color. It's charged, which means that gluons interact with gluons, whereas photons don't interact with other photons. And that has lots of consequences, but one very simple consequence is that the gluon-gluon interaction is attractive. And if you imagine what would happen if you try to make an extended gluon field, right, like we do in the electromagnetic interaction by taking 2 charges and separating them, then something different happens than in the case of E and M. In fact, if you do that, I've made a cartoon here. If 2 quarks are close, in fact, really it's a quark-antiquark pair whose potential I'm showing here. If they're close, the field around the quark is essentially Coulomb-like, right? And it's not so different from the electromagnetic interaction. But as you separate the quarks, the field interaction is attractive. And because it's attractive, the minimum energy configuration is where the field collapses on itself instead of being like that. And it essentially collapses into what we call a flux tube, where if you separate the 2 quarks, the field just stretches. But as you all know, right, what happens when you apply Gauss's law to this is that the radial, radially outgoing field, when you apply Gauss's law, gives you a 1 over r squared when you conserve the electric flux. But if you apply Gauss's law to this, because of the shape of the field, if you separate the quarks, the strength of the field doesn't decrease. Right? There's no sort of analog of the growth of the field integral with r squared. In fact, the field integral here would be independent of the separation. And so that means the strength of the field is constant. And if you evaluate the potential energy in the interaction, it becomes linear at large distance. So this is a model of the potential between really heavy quarks, because for light quarks, the potential is not very well defined. But you get the point, I hope, that at short distances, quark interactions look almost Coulomb-like, but at long distances they look very different. And in fact, they have a potential energy that doesn't go to a constant, but it grows linearly, which means that if you tried to pull two quarks infinitely far apart, it would take an infinite amount of energy. Which is why quarks don't exist as free particles in nature. They're actually confined into pairs like quark-antiquark pairs, and this is actually a output of a simulation looking at the field that confines a quark and an antiquark pair into particles that we call mesons. And so here's would be a quark, here's maybe the antiquark, and the field between them looks like what I've drawn up here. And then there's also particles called baryons, like the proton and the neutron, that are composed of three quarks in this configuration. And the systems that we observe in nature are hadrons that are either mesons or baryons. But the thing that is sort of fundamentally different about the strong interaction is this nature that the gluons couple to each other, and that changes everything. And one of the ways that it changes the physics is it leads to a property called asymptotic freedom. Now, to understand this maybe the best, I showed here a diagram that we use in particle physics to sort of sketch out how particle interactions look maybe if we scattered a quark off a quark at high energy. This is a useful intuitive tool, but it's also used for calculational purposes. And when we calculate diagrams like this, there's a factor that goes with each of the vertices. So this represents a quark interacting with a quark through the exchange of a gluon. The Q here, if you will, represents the momentum of the gluon. And this constant alpha S is the analog of the fine structure constant. It determines the strength of the coupling of the gluon to the quark. And what we learned back in the late 1970s is that coupling constant actually decreases rapidly with the momentum of the photon. Well, I mean rapidly in the sense that it goes from 0.5 here, and if you go out logarithmically in Q, it changes by an order of magnitude, let's say between 1 and 100 GeV. But unlike electricity and magnetism, the strength of the interaction decreases rapidly. And this was a big discovery. It led to the Nobel Prize a few years ago. And this property had some interesting consequences for thinking about the situation where you create many quarks together. In fact, as early as 1980, people realized that one of the consequences of this result would be that you could go to essentially the analog of large momentum transfer, essentially in the Fourier space, by going to short distance. Right? So if you could create a system of quarks, instead of scattering them at high momentum, if you could just make them, compress them to be at smaller distance, so maybe you put them under some pressure, you add heat, right, to produce maybe extra gluons, maybe more quark-antiquark pairs, you could create a system that would be sufficiently dense that you might actually change its properties into something else by going out and by essentially pushing out on this curve. Right? And that something else is referred to as the quark-gluon plasma. And this very naive idea is because of asymptotic freedom, it might be possible to do this. Okay, now that's a naive picture. It's not completely wrong, but it's naive. But we can do a lot better. And we can do a lot better because there is a way to calculate the physics of the strong interaction on something called the lattice. I'm not going to discuss the details, but the lattice allows us to study the thermodynamics of the strong interaction, and for example, do things like make this plot shown on the right, which is a plot of the energy density, epsilon, and the pressure as a function of temperature, except that there's a t to the fourth divided out because that's typically these quantities would scale as temperature to the fourth. And so you can calculate the equation of state, the relationship between the energy density and the temperature, the pressure and the temperature, or the relationship between the energy density and the pressure, and here are the results, right? And what you see is that over a narrow range of temperatures, the energy density and the pressure to a lesser extent, but the energy density changes by of order of magnitude over a narrow range of temperatures. And if this were discontinuous, it would be consistent with the first order phase transition like we're used to with water. It's not discontinuous, so it's a smooth crossover transition, but essentially around 150 to 170 MeV, and there's some uncertainty there. There's a transition from confined hadrons, mesons and baryons, up to a state where essentially the quark and gluons become released from the hadrons and become in principle dynamic particles of their own. On the left, I show a phase diagram that people think applies to the strong interaction. And essentially, this equation of state corresponds to looking along this axis where the temperature is increasing, but at 0 baryon density. There's interesting physics at finite baryon density, including the possibility of a critical point, but that's beyond the scope of this talk.
Does that imply that there is no separate transition for chiral symmetry?
Okay, well, that's a rather detailed. We don't know. All the indications are that, in fact, the deconfinement and the chiral symmetry transitions occur essentially at the same time, right? At the same temperature range, right? There's no necessary requirement that they do, but all the indications are that they're happening simultaneously.
But it's supposed to be a phase transition. The crossover is a finite size event.
No, actually, even on the lattice, right? So the lattice is the equivalent of infinite matter. Even on the lattice, it's a crossover transition at 0 baryon density. Now, at finite baryon density, out here, there is a first order phase transition, right? But at 0 baryon density, it is a crossover transition.
You're in the one phase region.
Yeah, right. Now, that also depends on the quark masses. It appears that for physical quark masses, especially, the strange quark plays an important role, that for the physical quark masses and the physical pion mass that we observe, it is not first order phase transition, but calculation suggests if you go to, really very light quarks, very light pion, it might be first order, but that's not the world that we live in. So it's apparently a crossover transition. Now, on the other hand, there's some really interesting physics associated with the difference between the energy density here and 3 times the pressure, because if you had an ideal relativistic system, those would be equal to each other, right? So if you had a relativistic ideal gas, then these two curves should be on top of each other. And if you take the difference, that's what's called the trace anomaly in QCD for the experts, and that's plotted on the right-hand side. And you see it grows to very large values right above the transition, so above 200 MeV, and then it starts to drop. So this quantity is somehow describing or reflecting interactions in the plasma, because it's 0 in the non-interacting or ideal gas limit, and you can see that it's actually very large right here near the transition, and that suggests that there's some kind of strong interactions occurring near the transition. And one of the interesting questions is, what are the implications of this decrease here? And there is disagreement in the theoretical community about what that means. There are some who think that that actually means that the interactions in the plasma are becoming weak, and in fact there are perturbative calculations able to describe this curve down to about twice the critical temperature. And that suggests that, in fact, we're really starting to approach the perturbative limit suggested by asymptotic freedom. There are others who argue that, in fact, there's still strong coupling up to very high temperatures, but that, in a technical language, that QCD is becoming conformal. And I won't try to explain more about what that is. And the reason people think that is that the lattice calculations don't, here's a Stefan Boltzmann limit that you would expect to get for the ideal gas, and the lattice calculations don't seem to be extrapolating to that limit. And this difference is actually consistent with expectations from an infinitely coupled system. So some argue that out here you're still infinitely coupled. And this is one of the questions that, while we can't yet directly access experimentally, we hope to be able to provide some insight on.
So does conformal loosely mean that it's still a critical phase, or not trivial?
No, I think in this sense, conformal means that the running of the coupling doesn't play an important role in the dynamics, right? So it's conformal in the sense that it's scale independent, right? Of course, we know that in QCD the running of the coupling is critical to the dynamics, but the argument is that in this temperature range, the interactions are so strong that the running doesn't influence the physics. I personally think that's nonsense, okay? But that is the argument made by some that in fact the interactions are still very strong out here. Now, so coming back to this picture, one thing to say is the estimates on the basis of those last calculations for the transition to the quark-gluon plasma would say that the energy density you need is about 1 GeV per femtometer cubed. Some early estimates based on measurements that we made at the LHC from events like this, suggests that the energy density is an order of magnitude higher, or actually an order of magnitude and a half, so that we're way, way, way above the transition. Okay, now there's another whole bit of physics I want to come back to here, and that is, how do you get from the initial state of two nuclei into having a bunch of particles that are then supposed to be in this plasma state, right? Because there's a big jump between the collision of two nuclei and this, and we need to know something about the physics in between. And I'm going to give you a very sort of naive view of that physics, which has been a big part of the theory community in strong interaction physics in the last decade. And it has to do with something called saturation. And to motivate it, I'll say, in collisions at the LHC, the nuclei are Lorentz contracted by a factor of 1,000. Right? So at a couple TeV, you put in calculate the gamma factor divided by roughly 1 GeV for the mass, and you get factors of 1,000. So the nuclei are highly Lorentz contracted, but the thing is, you can't Lorentz contract the low momentum modes because of uncertainty. So most of those low momentum modes are soft gluons that are as part of the binding of the constituents of the nucleus, and they can't be Lorentz contracted, and in fact they actually leak out longitudinally so that there's overlap between the gluons coming from all of the different nucleons in the nucleus, at least longitudinally. Then what happens is because of that, these gluons can recombine, and this is actually a calculation that appears in work by Al Mueller and others from some time ago that's then gone through many generations of evolution. But the idea is that you can get combinations of gluons from different nucleons that go together, and as a result of combining, their transverse momentum essentially grows. They're nominally collinear, but as they combine, they start to shift their transverse momentum distribution. And you essentially, so you have some transverse momentum distribution, the combination shifts it to the right, maybe even changes its shape, and as part of that, there's actually some scale that is determining the amount by which the transverse momentum distribution is shifting, and that is a new sort of self-generated dynamical scale in QCD that has nothing to do with the intrinsic properties of the field theory, but is clearly an emergent property from having the combination of these many gluons. Now, the idea is that if that scale becomes much, much larger than lambda QCD, the sort of typical cutoff scale for the perturbation theory, then you might actually be able to do perturbative calculations and understand what's going on here. Not only that, but it implies very large occupation numbers for these gluons, and essentially it would imply a nearly classical gluon field, as opposed to having few numbers of gluons that might be interacting. You'd almost be looking at the interaction of gluon fields, kind of like the interaction of classical electrical fields in the scattering of charged particles. And this has a lot of consequences. I'm not going to get into sort of the role of unitarity in QCD, but the expectation is that the particle production in the early stages of the nuclear collision are essentially coming from the emission of these kinds of gluons as the nuclei pass each other. Almost like a shock, the gluons get put on the mass shell. So starting from that, there's, I would call it a concordance model for the basic understanding of how these collisions go at the LHC and also RHIC, which is that you have these highly Lorentz contracted nuclei, they collide, there's this initial gluon emission from these very intense gluon fields in the incoming nuclei, and then something interesting happens that we're still only now understanding, which is it seems that those gluons rapidly thermalize, actually much faster than anybody expected, such that the system actually relaxes into a mode where it seems to evolve hydrodynamically for a long range in time, and then at some point it cools over the whole evolution, and at some point it has to turn back into confined hadrons, and so this is the final state where it freezes out into the tens of thousands of particles that we then measure in our detector. Now, I'll talk more about this in the following slides. The fact that the system behaves here like a very good fluid was a real surprise. So this actually came out of the RHIC program a few years ago, and I just sort of put up here a press release, not that that's the right way to think about the physics, but it illustrates the issues. Back in 2005, we concluded from measurements at the RHIC that we've created a new state of hot dense matter, and that instead of behaving like a gas of free quarks and gluons, as was expected, the matter created in the collisions appears to be more like a liquid. In fact, not just, I think the liquid here is maybe not the best word, but it looks like a fluid that actually has nearly zero viscosity. It's almost perfect. And in order for that to be true, the interactions among the constituents of the plasma, aren't like we might have naively expected. They actually have to be quite strong. Now, to make sense of that, we should talk a little bit about viscosity, because it's not so well understood typically in the physics community. I certainly didn't understand it before I got into this. In fact, I never thought I'd be talking about particle physics, viscosity as a part of doing particle and nuclear physics, but here it is. So what do we mean by especially shear viscosity? So the simple way to think about it is, you imagine, looking at, let's say, fluid between two plates, right? And you move one plate with respect to the other, and the fluid flowing between it essentially has a velocity distribution that, linearly evolves from top to bottom. But the fluid flows driven by the motion of the two plates. Okay, and that's how we think of sort of a typical, fluid in a, very simple example that you could do in the laboratory. Now, viscosity describes the ability of the fluid to transfer momentum orthogonal to the flow direction, right? And how can it do that? Well, a fluid is composed of particles. The particles have some random walk. They move around. And if the particles are capable of propagating essentially momentum in this direction while they're supposed to be flowing to the right, they have viscosity. And the more they're able to propagate momentum orthogonal to the flow direction, the greater the viscosity. Conversely, the smaller the viscosity, the less the particles are able to move and transport momentum. And if the viscosity would go to zero, right, then the particles would basically only be moving due to the local flow velocity. Okay, now in a real system, that viscosity typically scales with entropy density S. And in fact, the ratio of these two is a natural parameter. It has dimensions of h bar, but if we just take out the h bar, set it equal to 1, or work in natural units, then this thing is a dimensionless quantity, and it's a natural scale for describing the strength of the interaction in the system, because a smaller value of this means a shorter mean free path for the interactions and stronger coupling, right? And a perfect fluid would have zero viscosity or zero 8 over S. Now, the thing that's interesting about all of this is, or in fact, the potentially hard part of all of this is that we don't have good calculational tools, particularly in quantum chromodynamics, for strongly coupled systems. Strongly coupled systems are hard because perturbation theory typically doesn't work, and that's a real problem, except that nature has maybe surprisingly provided us a tool that is ideal for calculating the behaviors of strongly coupled field theories, at least certain kinds of field theories. And it's something that goes by the moniker ADS-CFT, stands for anti-de Sitter space conformal field theory correspondence. It's technical terms for being able to do calculations in string theory in certain formulations, and I'm not going to get into the details of what those formulations are, but calculations essentially in gravity and string theory, and the results of those calculations are essentially dual, or can be mapped on to calculations in certain kind of field theories, not strictly QCD, but maybe field theories that are similar to QCD. And one of the early results of trying to apply this correspondence to understand and in fact, why is that important? It's important because the correspondence is such that weakly coupled gravity, essentially like classical gravity, maps to strongly coupled field theory, right? So you have weak on the string side, weak coupling going to strong coupling on the gauge side, which allows us to calculate quantities in strongly coupled field theories, which we might have had no hope of doing without this unique tool. So Juan Maldacena started this. It's produced an explosion in the theoretical community, and there are people here who understand this actually much better than I do. But one of the interesting results from this program was a suggestion that there's a lower bound to this quantity, essentially a lower quantum bound, due to the fact that by uncertainty arguments, you can't make the mean free path for a particle shorter than a certain limit. Right? And that bound is essentially 1 over 4 pi. Now, there are actually some tweaks to this that there actually might be a slightly smaller value when you use quantum gravity on the string theory side, but this is a good enough number to set the scale for where you have a system that is behaving in a way that's completely determined by the quantum mechanics. And this 1 over 4 pi corresponds to infinite coupling in the conformal field theory. So this is an interesting number to compare measurements that we might do from the heavy ion program, and I will show you some of those measurements, but first I want to show you that something interesting is happening. So first, came out of a nice paper written by these authors showing a comparison of materials that we know of in nature at high pressure, like water, nitrogen, and helium. Typically, this quantity, eta over s, varies with temperature in such a way that it reaches a minimum at some, special point, and then it rises again, right? And that typically, is determining some special property of the phase, right? And you can see, the curves here for water, nitrogen, and helium. Now, this bound from ADS CFT is down here, right? It's 1 over 4.
What is this scale? What is this TC?
Well, it's whatever sets the essentially this critical point for the corresponding quantity, right? So essentially this determines in the helium where it's behaving in its most superfluid form.
So these pressures are right at the critical pressures.
Yeah, right, exactly. Okay, so the thing is, but the most important point is we have these materials that we know of, in the physical laboratory, and here is that bound, right? In fact, I've sort of drawn it here, but it's really supposed to be 0.08, right? Compared to, the minimum values you see here for these liquids of order 10 to 20. Okay, now, if you do perturbative QCD, so you do perturbative theory where you describe the interactions between quarks and gluons sort of at the single scattering level, you try to calculate what this quantity would be, you would get this curve with some big uncertainties shown by these bands. Okay, so there's a lot of uncertainty in what perturbative QCD would give you, but it gives you a large value, again, somewhere up around here. But the data from heavy ion collisions actually suggests, and I will show you some of this data, that the value is down here. In fact, it suggests that the value that is there in the quark-gluon plasma is within a factor of 2 of this minimum bound that's been predicted from ADS CFT. Now, so let's talk a little bit more about this. So first of all, I just want to repeat that there's been a tremendous explosion in the last decade, really even 7 or 8 years, in the use of what essentially is this string theory, gauge theory correspondence, also is often referred to as holography because of the way the physics works. And in fact, there's something from a popular physics article talking about how string theory may hold answers about the quark-gluon plasma. Maybe that's a little bit too ambitious because it's a complicated problem, but I will show you some results as we go along that are really pushing progress in understanding this physics, even if the gauge theory that is being used here is not strictly quantum chromodynamics. Okay. So now let's talk a little bit about actually what we measure. So here is the Atlas experiment. As I said, it's maybe the biggest and most precise piece of experimental apparatus ever created by mankind. What's shown out here in blue are muon spectrometers. I won't say much about those. And then inside are calorimeters that allow us to measure the energies of photons and electrons and other hadrons. And then deep inside are particles that allow us to measure the trajectories of charged particles bending in a 2 Tesla magnetic field. We can measure the curvature of the particles, we can determine their momenta, and do lots of things, and I will show you some of those things. And as I say, in lead-lead collisions, we're typically measuring tens of thousands of particles at a time. Now, a little bit about one detail of how we do these experiments. I won't say much about this through the talk because it's not that important, but just to give you some idea of how we make sense of this physics. one of the things you have to deal with in nuclear collisions is that, you know, there is a classical impact parameter when you have two nuclei collide, right? And we consider that, we call that the B. It's the transverse distance, you know, essentially perpendicular to the beam axis between the centers of the nuclei. Right? And we have no control over that. That fluctuates event to event. It's on the scale of, you know, tens of femtometers, right? There's no way that we can, you know, collide nuclei with that kind of precision. You know, it's many orders of magnitude off. So we simply get events with different impact parameter, and we come in with a variety. And what we want to be able to do is experimentally say something about, you know, maybe not what the impact parameter was, but what kinds of events we had. And we do that using the calorimeter. So this is deep inside Atlas, a sort of explosion of what I showed you, where we have great calorimetry sort of shown on the outside here. And the main thing is that it covers a large range of angles, and we have little, look like little detectors here. We call them forward calorimeters that measure at very forward angles, and these are what we use to essentially characterize what we call the centrality of the collision, because what we do is we measure the energy in these things, and the particle production in these collisions goes over essentially all angles, but a lot of the particles just geometrically go into this region. And what I've plotted here is many millions of events, the energy that we measure in these calorimeters, and so here it is, this is the energy. Note the scale is in TeV, right? So this is 3.5 TeV of energy that's dumped into these little calorimeters. On this axis is the energy in the entire rest of the detector, right? And you note the scale up here, 10 TeV. Right? So these collisions are producing tremendous amounts of energy, right, over all angles, but we use the energy along this axis to distinguish events that look like that, where the lead nuclei pass through each other, you know, with a large impact parameter, from events that look like this. Okay? I'm not going to say much more about that, but it's important for one of the next couple slides. And so experimentally, we distinguish between these kinds of events, essentially by measuring the number of particles or the energy produced in these little calorimeters.
Is the right big impact parameter or small?
This is small, right? So small impact parameter is where they're head on, right? And large impact parameter is here. Okay, now, how do we know that the quark-gluon plasma is strongly interacting, right? So I've told you that it's strongly interacting and that this eta over S is near this 1 over 4 pi bar. How do we know it? Well, here you see it. This is one event. So one lead-lead collision where we've taken the energy measured in those calorimeters and just projected it all onto the azimuthal angle axis, right? So this phi is azimuthal angle, you know, 0 is that way, and you know, pi is that way, and we just measure the energy as a function of angle, and you see this huge modulation, right? Which, from the point of view of particle physics, makes no sense, because normally in particle physics, there's an azimuthal symmetry. There's nothing to break the symmetry, except sometimes spin, right? So normally you would get, you know, except for fluctuations, you would get a angular distribution that's uniform. Well, this is anything but uniform, and it means, and in fact this happens many, many events, so it means that there's something that's breaking the azimuthal symmetry and giving rise to this big modulation in the particle production. Well, what breaks the symmetry is if you have collisions that are at finite impact parameter. I draw a little cartoon here of what those collisions look like. All the energy is being created in the region where the lead nuclei are passing through each other. Out here, nothing really happens. And we know that because of the short range of the strong interaction, and also from, you know, many years of doing this physics, we understand that essentially all of the action is occurring here. But in that region, there's actually a spatial anisotropy, because the overlap, you know, the length of the region in this direction where the particle production is occurring is greater than in this direction. And so the dynamics of the heavy ion collision, essentially the finite impact parameter, breaks the azimuthal symmetry, right? Because the length scale here is longer than the length scale there. Now, of course, if the particles coming out of these collisions didn't interact, that would be meaningless, right? They just free stream. The size of the region in which they came from wouldn't matter, and we wouldn't see this effect. But they don't come out without interacting, and in fact, in order to get this effect, what you have to have is you have to have pressure developed by the particles themselves such that the pressure gradients, which are greater in the short direction than in the long direction, give rise to push that pushes the particles this way more than that way, and then enhances the particle yield here and here relative to there and there. And there's lots of reasons that we know this is the right thing, but let me just show you an analogy, completely different physics, that shows exactly the same effect. People have been studying ultra-cold atoms for some time, and in fact doing physics very similar to what we're doing by basically subjecting them to a magnetic field. And with the right magnetic field, you can actually make the interaction among the atoms at low temperature very strong by essentially tuning the magnetic field to put them at something called a Feshbach resonance. And you can actually adjust the strength of the interaction between the atoms so that it's either weakly or strongly coupled. And this is actually a nice picture of atoms that were put into a trap and confined in a trap in a way that their initial distribution looked a lot like that. It's longer in this direction than in that direction, held there, and then let go, right? And when they're let go, this time-elapse photography shows you what happens, right? The system is growing, it's expanding in both directions, but if you go from here to here, you notice it's expanding much more rapidly this way than it is this way. Right? So the size of the region this way is actually not really changing much at all, but it's exploding in the sideways direction. Well, there's every reason, all evidence suggests that the physics that we're seeing here is essentially the same effect from the initial state of the heavy ion collision doing exactly the same thing. That the pressure is pushing the particle production out sideways. Now, but we can do better, because we can actually use real calculational tools, not a model, but real rigorous theory to test this. And that rigorous theory is hydrodynamics, which, at least for ideal hydrodynamics, is very simple. You start with a set of initial conditions. You put in energy momentum conservation, which in a very formal way means that you write down this thing is equal to 0, but it's basically just a way of conserving energy and momentum. You can put in an equation of state. Here's the equation of state from the lattice I showed you before. And then basically you write out the energy momentum tensor in terms of the energy density, the pressure, and the four velocities as a sort of standard formulation, and solve it numerically. And if you do that, it already ran once, but let's see if I can get it to go again. Right? This is what you get for the simulation of a heavy ion collision at 0 impact parameter. Now, I have to say that I've actually cheated a little bit, because this is actually hydrodynamics with viscosity in it, so it's not ideal. And in fact, there's been a major revolution in the last few years in viscous hydrodynamics, being able to do it in a system where relativity is important, which is true for these collisions. And essentially, the people who have been doing this, the theorists, have really made a sort of tour de force improvement in our understanding of viscous hydrodynamics. Now,
what are the colors?
Density. This is energy density, basically. Right? So if you just look at the energy density as a function of time, both in essentially the receding nuclei and in the energy that was left over in the middle. Now, this is for 0 impact parameter, so it doesn't really show you the physics, but in fact, if you do calculations from this hydrodynamics of the amplitude of this modulation, right? So I showed you the modulation that we observe in one event. You calculate the amplitude, and you can plot it as a function, for example, of the momentum of the particles. Okay? Now, there are data points here, which are in the black points. In fact, there are different sets of data corresponding to measurements from the Lattice experiment. Those are shown in the black points, and actually measurements from the program at RHIC, which are also shown under here, but it's a little hard to see. And then there are different curves, right, that are essentially calculations using the hydrodynamics with different values of eta over s. Maybe I'll focus you on the right-hand side, which is a similar plot of the modulation. But first of all, you can see the calculations are getting roughly the right PT dependence, and this is, this is not trivial. In fact, getting this right dependence on the momentum of the particles is non-trivial, and in fact, very good evidence that the description that I'm giving you is in fact correct. On the right-hand side, I also show as a function of essentially this variable that we use to determine the amount of overlap between the nuclei. And if you look at the RHIC data here, and look at the purple curve, that corresponds to an eta over s of 0.16. That's roughly 2 over 4 pi. Now, if you look at the data from the LHC in the black points, right, and the curve that goes through it, that's actually somewhat larger. Instead of being 2 over 4 pi, it's more like 2.5 over 4 pi.
Don't we jump from hydrodynamics to PT?
Because in hydrodynamics, you can actually do the freeze out and get the transverse momentum distribution of the particles, right? So essentially, you're mapping.
Is it highly non-trivial to do the freeze out here?
There's really nothing because if the hydrodynamics, I mean, there's an interesting question about what the hydrodynamics is doing at early time, but at late time, right, the hydrodynamics is really only going to work if the distribution of particles is isotropic in the local rest frame, right, and then doing the freeze out into either quarks and gluons, or these calculations actually do freeze out into hadrons and then actually run a later kinetic calculation on the interactions of the hadrons. It's a detail. But the freeze out is...
Hydrodynamics terminates when you hadronize?
It terminates when you essentially make the transformation from the fluid description into a particle description. And there are very well, let's say...
But doesn't happen, I'm asking, when you hadronize?
You can do it either way, right? So you can do it at hadronization, and most of the calculations do it actually at hadronization. But you can also run the calculation through hadronization. If you do that, you just have to be careful because the assumption of chemical equilibrium through hadronization isn't perfectly hold, right? So you have to correct for chemical effects if you run the hydrodynamics through the hadronization, but you can do it. So this calculation actually basically runs it to freeze out, to hadronization, then runs a calculation of the hadron transport after the fact. But all of the physics here is essentially in the deconfined phase, right? All of the buildup of this flow that gives you the expansion is coming from the deconfined phase.
I don't fully understand that plot. So you had, for one event, you had this modulation.
Right.
And that plot, I should think of it as like making that plot in slices of PT.
Yeah, and you can do it over many, right, so you can select many events and of course average over them. Now I'll show you where in fact this is actually typically averaged over many events. We're doing a big step in Atlas in doing this event by event, which I'll come to in a couple slides. But this is typically averaged over many events, but then selecting on the transverse momentum of the particles.
But PT, it's not PT of the system.
No, it's really the momentum of an individual particle, right? So there's a suggestion here that there is actually a change in this eta over s quantity between RHIC and the LHC on these numbers. However, I should say that beware, there are hidden theoretical uncertainties I'm not going to try to get into. And clearly one of the things that needs to be done is to do more precise constraints on the hydrodynamics. So how do we do that? Well, one of the things that you can do is take advantage of the fact that in the initial state there are quantum fluctuations, right? So that cartoon I drew you of the nuclei overlapping and the spatial region over which we produce the initial particles, the energy density being anisotropic. Well, but on top of that there are quantum fluctuations, right? So this is a cartoon of, imagine the initial state with quantum fluctuations, and in addition to that twofold modulation, it actually goes like cosine of 2 phi. There are higher harmonics that will result from these initial state fluctuations if the system preserves essentially is not too dissipative. Okay, so these initial fluctuations, if the system doesn't have too much dissipation, will survive to actually influence the angular distribution of the final state particles. And you can actually write down essentially the differential as a function of the momentum of the particle, its what we call the pseudo-rapidity, and its azimuthal angle. You can write that into a Fourier series in the azimuthal angle. Now, for each essentially harmonic, there's potentially a different phase. So this is the phase angle for each harmonic. That's a detail. But the point is that you can measure the amplitudes of each of the Fourier moments. And to show you that there's something non-interesting here, I'll show you this result. This is actually done using two particles, taking pairs of particles and looking at their opening angles. So it's a little bit more complicated, but nonetheless you can see that there's complicated modulation reflecting the effect of these initial state fluctuations. And you can actually see the decomposition of this black curve, which is essentially the Fourier analysis of the data shown in the open circles. And the odd harmonics are shown with the purple curve, the even harmonics are with the blue. And they're all there. And in fact, you need several harmonics in order to describe this full variation.
Is this one event?
This is average over many events. I will show you what happens when we do it with one event.
Why don't the fluctuations average out?
Because when you do it with pairs of, so the thing about this with pairs of particles is that the pairs from the same event have information about this angular distribution that you can't get rid of, right? In other words, if you look at the opening angle between pairs of particles and you take many of those pairs, even if you average over many events, right, that information is preserved. Okay, so if you just tried to do the single particle angular distribution averaged over many events, you can actually do it if you measure this phase angle event by event, and we know how to do that. But the two particle correlations actually preserve the information from each event, even when you average. Now, in fact, if you look at the amplitudes of the Fourier moments, they look something like this. So this is as a function of the Fourier's power, the harmonic, right? So 2 would be the cosine 2 phi, which is the thing I showed you before. Then there's 3, 4, 5, 6, and 7. And what you can see is that the amplitudes are doing something like this, and we're getting non-zero amplitudes up to n values of order 5. And in fact, this is for particles with relatively low momentum, and then as you go up in the momentum of the particles, what you see is that, in fact, the higher moments, like the n equals 3 moment, start to dominate over even this n equals 2 moment. And what that's saying is that the higher PT particles are actually picking up a larger contribution from these initial state fluctuations. Now, the question is, what can we do with this? Well, first of all, I just want to tell you that, in a sense, what we're doing is here, we're looking at the angular distribution of particles coming from initial state fluctuations, which is not so different from what's happening in the early universe when we do cosmic microwave background measurements. We're essentially measuring the fluctuations that occurred at early times in the evolution of the universe that have been preserved through the evolution of the universe. Much of that evolution can, in fact, be described by hydrodynamics to the final state, except that right now we're only doing it in one angle, one dimension in angle instead of 2 dimensions. Now, in fact, a big step recently is to be able to incorporate these fluctuations in the hydrodynamics. In fact, so we're doing calculations that look like this and actually look at how these fluctuations are preserved through the viscous evolution, and the greater the viscosity, the less the initial state fluctuations will survive, because higher viscosity means more dissipation. And maybe the best way to show the utility of the data is, this is actually maybe the most rigorous attempt so far to take atlas data that I showed you on previous slides and fit it to try to extract information from eta over S. Now there's one issue, a detail, which is that we have to know something about the initial state fluctuations, what those quantum fluctuations are, and there might be different models of those. So I'm showing you different calculations that have different assumptions about the initial state fluctuations, and then essentially taking those, running them through the hydrodynamics, comparing them to the data. So the data on the right-hand side are the values of this amplitude as a function of n. So you can see the data points here in green and then the different calculations compared. And if you do a chi-square fit, the typical models are saying we're somewhere around 0.16, 0.17, which is a little bit above twice this 1 over 4 pi limit. But you can actually do much better, in principle, by doing this physics event by event. right? And so that's actually something what you've been asking is, can we do this without averaging over many events? Can we do it event by event? Well, these are plots of the angular distributions of particles in 3 events. So the top are just the straight angular distribution, right? You take an event, you plot, the azimuthal distribution of particles reconstructed in the tracking detectors, and you see these big variations which are not statistical, right? You can see the error bars. They're clearly, big variations as a function of phi, and they clearly have more complicated harmonics in them. The bottom is showing you, if you take pairs of particles and look at the opening angle between pairs of particles, you're essentially convoluting this distribution. You get more precision that way on the lower moments, right? So you can see here clearly the dominance in this event when you look at the 2 particle correlations of this, what we call the elliptic physics. But for example, in this event, when you look at the 2 particle correlations, you see not only the cosine 2 phi, but you see these peaks which correspond to the cosine 3 phi. And the point is that we can actually do this now event by event. And this is actually a breakthrough by those of us working on Atlas. And we can actually measure the distributions of these moments, the amplitudes of the Fourier terms, over millions of events. So for example, this is the 2nd Fourier coefficient, the 3rd Fourier coefficient, the 4th Fourier coefficient. The different colors represent different amounts of overlap between the nuclei. And you can see how the probability distribution of getting a value in a particular event is changing as you go. For example, this green curve is where the nuclei are nearly head-on. And when the nuclei are nearly head-on, this second moment is actually not determined by the geometry at all. It's actually determined by the quantum fluctuations. And in fact, this is really just a 2-dimensional Gaussian, because this quantity, the Fourier moments, are really in 2 dimensions. So this is just a 2-dimensional Gaussian. In fact, the 3rd and 4th moments are almost completely determined by fluctuations and are well described by 2D Gaussians, which are the solid curves. So in fact, the initial state quantum fluctuations are dominating the higher order harmonics. The second harmonic, when you go to larger, this value what we call centrality, but means larger impact parameter, then you see it gets really shifted out to larger values of the amplitude, and that corresponds to the geometry, right? And so this is where just the simple geometry of the initial state collision is giving us large collective motion in this harmonic, but in the higher harmonics, it's really completely determined by the initial state fluctuations. Now, the next step you want to do is be able to compare that to the hydrodynamics, and in fact, this is, if you will, maybe the most complete calculation that's ever been done of this problem, which is simulating the initial state, simulating the hydrodynamics, putting in the correct lattice equation of state, doing the Hadron essentially transport afterwards, and then calculating what the event-by-event distribution of these quantities looks like and comparing to the data. Now, in fact, what's really shown here is a ratio with respect to various kinds of averages. And I don't want to go into details, but the thing to do is compare the solid points, which are in black, to the red curves, which are the theoretical calculations, and in fact, there's 2 sets of data here. One where the nuclei are nearly completely overlapping, and one where there's a finite impact parameter. And the distributions are different, particularly for the second coefficient, which is determined by the geometry of the overlap. But in fact, you see that the hydrodynamic calculations are doing maybe, plausibly good at actually describing the data. There might be some reasons why they're so good, but in fact, we're able to describe this very detailed set of measurements with an eta over s that's roughly around 2.5 times 4 pi. So in fact, we have really precise measurement of what's happening with both the initial quantum fluctuation, with how the initial quantum fluctuations are propagating to the final state by being able to do these measurements event by event. And this is something that's really only happened in the last year. I'm going to skip the next slide, but I want to come back to it. But what I want to do is tell you that there's been a recent surprise that may help us understand why this works so well in heavy ion collisions, or at least explains how we go from this initial state of gluons being emitted from this high-intensity gluon fields to a final, well, not a final, actually, to within a very short time, a system that behaves almost hydrodynamically. So, in fact, what we went into doing these measurements was to look for this thing that I called saturation, which is really an effect of having these real intense gluon fields. And the way we intended to study that was to not collide two nuclei, but to collide a proton with a nucleus. And the expectation was there that we wouldn't produce the quark-gluon plasma and all of the effects that I showed you above and a lot more that I haven't shown you, but that we would be able to probe the particle production coming from the really intense initial gluon fields. In fact, we expected that we would be able to understand that physics almost using perturbative calculations. Okay, so here's an event with a proton coming from the right, colliding with a lead nucleus coming from the left. You produce lots of particles. You actually produce more energy in the lead direction than in the proton direction, which you can see here as the energy represented in the lead going side compared to the proton going side. So this is a typical event with a lot of particles, and this was considered the ideal laboratory for probing the effects of having these intense gluon fields in the nucleus. Okay, so now one of the things that we did was to do something analogous to what I showed you in lead-lead collisions, but to look at the angular correlations between pairs of particles to do various things, but that's what we did. Just to be clear, there's a variable that we call pseudorapidity. It's defined like this in terms of the angle, the polar angle of the particle. The reason we use this quantity is it's approximately something called rapidity. Some of you may know rapidity, maybe if you don't. Rapidity is a variable that adds under Lorentz transformations along the beam direction like this, such that distributions in rapidity basically retain their shape and they just shift. And it's a very useful variable for understanding the physics. So what we did is we took pairs of particles from the event and we looked at their difference in azimuthal angle, so this way, and in rapidity, and we plotted it. And so this is what you see. Okay, now these events on the left are low multiplicity. These events on the right are high multiplicity. First, what I want to do is focus your attention on the low multiplicity events. This big peak, where there's correlated particles, is a result of jets. What I showed you in the second slide, where you get very high regions in the energy density in this two-dimensional plane of pseudorapidity and azimuthal angle. And this peak comes when you get lots of particles produced all at the same angle, essentially where the rapidity separation and the azimuthal separation is 0. Okay, so this big spike is really just the physics of hard scattering between quarks in the incoming nuclei, producing correlated and collimated sets of particles. So that's nothing new. Now, but when you get jets, you typically get them back to back, right? So you have to conserve momentum in the azimuthal direction. So, if the collision is this way, if one jet goes there needs to be another one on the opposite side. But they can spread out in rapidity, so the two jets don't necessarily appear at the same rapidity. So if you take a hadron from one jet and a hadron from another jet, you'll see pairs that are at an azimuthal separation of pi. So pi is around 3, but they'll be spread over a large range of pseudorapidity. And that's also standard. There's nothing new about this. So when we look at low multiplicity collisions of proton and lead, we see basically the signature of jets, and then this is the signature of back-to-back jets where you pick a particle from one and a particle from the other. So there's nothing interesting there. But what's interesting is that when you look at the proton lead, in addition to those features, you see this long-range correlation at small relative azimuthal angle. And in fact, this had been seen by CMS in proton-proton collisions. Some of us, especially me, didn't believe it, but it showed up very easily to see in proton-lead collisions. It's called the ridge sometimes because it looks like a long-range ridge in pseudorapidity. But there it is. I mean, you just do this measurement with high multiplicity events, and it pops right out. So the surprise was that we wanted to figure out a way, we in Atlas in particular, when we saw this data, we wanted to be able to remove the effect of the jets, right, and see what's left when you take out the jets. Because in this distribution there's a jet, there's the dijets here. We wanted to take it out and be able to see what's left. So when you do that, basically what you do is you measure, this distribution in the low multiplicity events, and there's a way of subtracting it out from the high multiplicity events. And when you do that, you're left with this. You see essentially something that modulates in azimuthal angle in a way that looks almost identical to what I showed you in lead-lead collisions. And it basically has no variation with pseudorapidity or with polar angle. So basically it means that, as you change the polar angle, this feature looks identical. There's a little bit of the remnant of the jet. That's a detail, and I won't discuss it. But you see something that looks really remarkably similar to what we saw in lead-lead collisions. In fact, this looks like that collective effect that we saw in lead-lead collisions coming from the pressure built up in the quark-gluon plasma because of its strong coupling. But there's no reason that it should have been here, because these proton-lead collisions produce a much, much smaller system. We didn't expect there would be any collectivity there, and yet you see this. Now, I should say that there are some theoretical calculations that actually invoke the saturation that I described, where the gluons in the nucleus essentially recombine in the initial state. And there's a set of calculations that shown in gray here that actually can reproduce the data. Maybe I'll focus you on the left-hand side. This is a projection of that distribution that I showed you on the phi axis. So the data essentially do this between 0 and pi, and then, if you will, if you go to 2 pi, it just does it again. And the modulation that I showed you is here, but the calculation seems to be able to describe it, but it's really, that modulation is not coming from this physics of the intense gluon fields, really. It's just coming from some assumptions of the wave function that were put in order to explain the ridge that was there observed in proton-proton collisions in a similar way. So it's really not intrinsic to the physics, and in fact, I think many of us are skeptical that this is actually the right explanation. On the other hand, first of all, I want to just say that there's a different set of measurements shown here that actually use many particle correlations, in this case typically 4, where you can take out the effects of the jets, let's say more robustly, and measure the analog of this flow coefficient, the Fourier moment, and the data points for that are shown, for example, here in black. Right? And this is in proton-lead collisions, right? And this scale that we're seeing of around 0.07 is only about 30% lower than what we see in lead-lead collisions, right? So it's a huge effect, right? It means that there's a modulation in the final state of the particles in proton-lead collisions, which is nearly as large as what we see in lead-lead collisions. And the thing is that there are some calculations here shown in blue that are using hydrodynamics. The green are also using hydrodynamics with some different assumptions that are actually able to reproduce the experimental data. And in order to do that, they need a quantity, this eta over s parameter, to be actually much closer to 1 over 4 pi. In fact, this is the range that they use, and 0.08 is really 1 over 4 pi. In fact, more recently, there have been measurements by, so that I don't focus only on Atlas, by the CMS experiment and Elliptic, which is a dedicated heavy ion experiment. This plot I picked from CMS is the third harmonic. There's really no natural way for the saturation calculations to describe a cosine 3 phi modulation, but from the initial state fluctuations, you would naturally get it. What's shown here is as a function of the multiplicity of particles in proton-lead, sorry, it's so close I have to keep track. This is proton-lead here. This is lead-lead collisions. Now, lead-lead collisions with only 100 tracks are a very special set of lead-lead collisions with very large impact parameter, but you can select them. And in those collisions, you can measure this third Fourier harmonic. You can do the same thing in proton-proton collisions, essentially, and compare at the same multiplicity, and compare the value of the harmonic, and they're remarkably similar. Okay? In fact, these two distributions look more like each other than they have any right to. And even more is, Elise has done a set of measurements where they've changed the mass of the particle, so they use pions that are in red, kaons that are in green, and protons that are in blue. And that's interesting because if you have a collective expansion of the system, right? The expansion is essentially in a velocity, and the translation from velocity to momentum is different for the different particles. And so if the effect were coming from collective expansion, you should see a difference in the way this amplitude of the modulation varies with momentum. And in fact, this breaking of the protons, kaons, and pions is precisely what you would expect if you had a velocity-determined expansion producing the modulation. So I have to say, I mean, this is preposterous as far as I'm concerned. A year ago, when we first started doing this, I would never have believed that in proton-lead collisions we could be seeing collective effects, but all of the data are pointing in that direction. So to summarize, first measurements at the LHC combined with previous measurements at RHIC and ongoing measurements at RHIC have really stimulated rapid development in understanding the transport properties of the quark-gluon plasma. This quantity eta over S is only one of them, but in particular, understanding the response of the plasma to the initial state quantum fluctuations gives us more precision on this eta over S, and we're finding that it's really close to this quantum mechanical lower limit. And in that range, the physics is clearly strongly coupled, and that's where the string theory, gauge theory correspondence is actually providing new insights, and in fact, really driving the development. It was actually using the ADS-CFT correspondence that provided one of the major steps forward in solving the problem of viscous hydrodynamics, or relativistic viscous hydrodynamics, to give us guidance on what terms should be included. And in fact, I'm going to go back in a second and show you one slide on even understanding how hydrodynamics can be applied at very early times. But on top of all of this, right, the expectation is that we could understand the physics of the initial gluon production by studying proton-lead collisions and constrain the initial state. But in fact, what we're observing is that even the proton-lead collisions are exhibiting the same kind of phenomena. In fact, it looks like the final state in a proton-lead collision is exhibiting collective behavior consistent with a strongly coupled system, which nobody expected, at least very few people expected, and it was really unexpected, and in fact I think is suggesting that strong coupling is ubiquitous in QCD, at least for long wavelengths, right? Because those systems do not have the large distance scales for a system to evolve for long periods of time and develop strong collectivity. The typical transverse size is just a femtometer or two, and for even that small size system to exhibit this collective behavior must mean that the strong coupling we're observing in the quark-gluon plasma is actually ubiquitous in QCD. And maybe this is one of the reasons that we're able to actually have a rapid evolution from this initial gluon production to the quark-gluon plasma phase, actually more rapid than people expected. And I skipped one slide. I just want to take a minute and go back to show you how we're using ADS-CFT to even better understand this. The set of calculations that started a couple years ago trying to mock up the collision of two lead nuclei, actually by colliding world sheets in essentially gravity, right, and then looking at the analog quantities in gauge theory. And so here's essentially a cartoon of essentially two incoming world sheets that interact, then they go out, right? And one can use essentially the string theory, field theory correspondence to understand what's going on in this system when the coupling is strong. And you can ask the question, is it plausible that you can take a system and get it to essentially turn into a mode where hydrodynamics applies on the timescales that we observe at RHIC and the Large Hadron Collider? And the answer is basically yes. And one of the surprises that's come out of this is that the hydrodynamics actually seems to apply even before the system truly thermalizes. So normally the way hydrodynamics is supposed to work is you need an equation of state, which means you need thermodynamic quantities like temperature and pressure and so forth, and that means that there has to be local thermal equilibrium. But in fact, if you will look at the calculations in this strongly coupled field theory at very strong coupling, it appears that the hydrodynamics actually applies before the system is truly isotropic. And I won't go through the details, but there's a plot here which looks at essentially the ratio of the longitudinal and transverse pressure. Those are the things that are most out of equilibrium at the beginning. And on time scales of typically 0.1 to 0.3 femtometers over C, you're essentially in a situation where the expansion of the system, driven by the velocity of light of the incoming nuclei, is basically, essentially matching in terms, is balanced by the interactions of the system, such that you're starting to get hydrodynamic behavior even within a few tenths of a femtometer over C, and that the hydrodynamic behavior sets in very shortly thereafter. But in fact, there are new calculations that are trying to describe the hydrodynamics when it's anisotropic, and in fact find that they can actually describe, at least in this strong interacting system, the evolution from anisotropic hydrodynamics to normal viscous hydrodynamics in a smooth way. So this analysis, taking advantage of our unique tool for understanding field theory at strong coupling, is actually pushing our understanding of the way hydrodynamics is applying in a regime which is, I think, never been encountered before in nature. So this is really new, and in fact, I would say it's probably has yet to been incorporated into any of the comparisons with the data. I'm expecting, that over the next couple years, driven by results from the LHC and driven by our ability to use these tools from string theory, we're going to have, continued evolution in the understanding of the nature of this strongly coupled quark-gluon plasma. Now, I didn't tell you about a whole lot of interesting physics, where we can look at how quarks propagating through the plasma lose energy through something called jet quenching. That's where I do most of my work. And one of the interesting parts of that is to probe the plasma on short distance scales and short wavelengths, where everything I've described to you today has been sort of on long distance scales, long wavelengths. And there are hints that when you probe the plasma at short wavelengths, it looks weakly coupled, while on long wavelengths, it's strongly coupled. And that would be compatible with our expectation of QCD, that you're actually seeing sort of the running of the behavior of the system, whether you look at it on a long scale and a short scale. But that's maybe a bit too soon, and will come out in a couple of years in the future. So let me come back to my conclusions. Let me just say, the big picture. QCD is described by a fundamental Lagrangian, right? And in that Lagrangian, there are parameters like the charge strength and masses, and that's it, right? And the perturbative limit of QCD is very well studied, but the physics I told you is providing a laboratory for studying QCD in a regime where perturbation theory doesn't apply, but there's a whole set of emergent physics that just doesn't appear in this Lagrangian, like the strong coupling, possibly we're still not completely sure we're understanding the physics of the high gluon field strength, because maybe it's getting mixed up with the strong coupling effects that we're seeing in the final state. But these are things that we can't study in any other way. And I should say that QCD is the only non-abelian theory whose thermal and multiparticle behavior we can study in the lab. Already it's showing interesting results, and I expect that will continue. Okay, thank you.
So maybe time for just one or two questions. Yeah.
Could you go back to the projection of the phases? The E over T to the fourth and P over
Yeah. The equation of state.
Right.
Yeah.
Thank you.
There.
Yeah, exactly.
Or this one. How about that one? That's even better.
The one on the left.
Yep.
There. That's a lattice QCD calculation, is that right?
Yeah, that's correct.
That quarks. That's just.
No. This is with dynamical quarks.
Oh, wait.
Yeah. So I mean, I should say
Where's the Stefan Boltzmann limit there now?
so that's the interesting thing, is it's up here, right? So the Stefan Boltzmann limit is there, and if you see the calculations are, asymptoting to something significantly less than the Stefan-Boltzmann limit.
I see. So it's claiming it's not going to the Stefan-Boltzmann, and that's where you see the evidence for strong confidence.
Well, okay, so exactly. So that has,
Close, even if it's not.
well, and the interesting thing is if you do this ADS-CFT in infinite coupling, you get that these should approach 3/4 of the Stefan-Boltzmann limit, which is not too far off from this. However, one should say that there are still technical issues in in these calculations that are being worked through by the Lattice community, and in particular, right, these calculations were giving a transition temperature, which you can see here is around 190 MeV. And in fact, in the last year and a half, that has gone down to 150 MeV. I would say there are in the last calculations, and there are potentially finite lattice effects that are determining, this asymptote. Now, those are estimated here in black, but I would say the jury is still out on exactly, what the right extrapolation here is. But if you look at this and you take it at face value, you would say that's strong coupling, right? Because it's not going to the Stefan-Boltzmann limit. On the other hand, there are perturbative calculations, so using thermal field theory, of the trace anomaly, right? In fact, I have a plot. There are perturbative calculations of that trace anomaly that are able to do very well down to twice TC. Just get there. Sorry. Yeah. There it is. Right. Oh. There are perturbative calculations, now, albeit with big uncertainties, scale uncertainties, but here is a set of thermal field theory calculations. So the red line is the central value, the uncertainties are big, but essentially getting pretty well the evolution of the trace anomaly down to low temperature. And this is why I say that there's real sort of disagreement in the community about whether the physics up here is strongly or weakly coupled. And this is a place where we can't measure the equation of state experimentally, but we can constrain. Ultimately, we think we'll have the precision to constrain whether or not the strength of the interaction is getting weaker as you go up in temperature by putting constraints on the temperature dependence of eta over S. The problem is that the lattice can tell you thermodynamics, but it can't tell you dynamic quantities like eta over S yet. And what we don't know is whether this is saying that eta over S should become larger, or because the interactions are becoming weaker, or whether this is, whether it's strong coupling all the way and eta over S shouldn't decrease. There are hints from the data that the strength of the coupling in the plasma is getting weaker as we go up in temperature, but we need more precision in order to make that convincing.
That's not lattice gauge calculation.
No, this is perturbative thermal QCD with some resummations that come under the moniker of HTL. This is lattice. This is perturbative thermal field theory in QCD. And so they're completely different, right? This says strong coupling. This says weak coupling, and we don't know which is right. Right? And that's something that is really an open question in QCD that we should be able to actually shed some insight on by doing the measurements and actually probing the physics that's hidden underneath these thermodynamic quantities experimentally.
So why does it say weak coupling? Because you say it's extrapolating to 0?
No. It's because this red line is thermal field theory, right? It's not Lattice QCD, it's just thermal field theory, right? And it's describing the lattice calculation. So I'm sorry, the data here are from the lattice, right? And the red line is just pure thermal field theory, right? So it's perturbative with some resummation, and if it's able to describe the lattice data, right, that would imply that the weak coupling is what's going on.
Well, we had a few hands here.
Yep.
Please.
Yes, I would like to know whether the lower bound on eta over S using ADS correspondence deals with real QCD or some variation of like supersymmetric?
Well, it is not real QCD. It is supersymmetric theories, but a wide class of such correspondences to different kinds of conformal gauge theories basically give you the same bound, right? So in fact, I think it's believed that the classical gravity to conformal field theory correspondence, that the 1/4 pi is really correct, that it's really a lower bound. Now the question is, if you go beyond classical gravity on the string theory side, can you actually get a lower bound? And there are indications that if you basically do quantum gravity on the string theory side, and this is beyond my understanding as an experimentalist, but using Gauss-Bonnet gravity, that you can actually get a slightly lower limit. I think instead of 1/4 pi, it's more like 1/6 pi. Okay, so there's slightly, and I would say that's maybe less certain than the classical gravity limit of 1/4 pi. But if there's a difference between those two, it's modest, and I would say most people think that the 1/4 pi is at least a reasonable scale, right, for what infinite coupling should give you, and maybe the true limit is actually lower than that. But the fact that we're seeing values for 8/s that are close to even the 1/4 pi is really saying that we're seeing something that has very, very, very strong coupling. And maybe one would hope even in the future we would be able to experimentally test whether we can push down below the 1/4 pi or not. We'll remain to see whether we'll have that kind of precision.
Okay, maybe one more. Great, no? All right. Well, let's thank Brian.
Okay, thank you.